Okay, so let's go ahead and go through the second part of this one. So first of all, we want to find hafnium on the periodic table. So did you guys figure out what the atomic number is? It's 72, so it's hiding over here. So just as a quick review, Gen Chem. So if its atomic number is 72, what does it have 72 of? Protons, and as long as it's neutral, also should have 72 electrons. So what you want to be careful about is when you go back to the noble gas before it, what's the noble gas before it? Okay, but notice that since xenon only has 54 electrons, you're going to go through to barium, but then you also have to go through the entire F block here to make sure you have enough electrons. Okay, so make sure you're paying attention to how many total electrons and you're not skipping through the F block. So if we were going to write this out, we can absolutely use the noble gas xenon. So what electrons do we have after that? 6s, how many of those? 2. Then let's go ahead and go through the F block. What's the principal quantum number for that F block down there? This is what number F? Yep, that's the 4F. And how many electrons in there? Yep. Okay, and then where do we have to go to actually get to hafnium? 5D, how many? Yep. Okay, so first of all, any questions about why that is the electron configuration for hafnium? Any questions about where any of those numbers are coming from? Okay, so as long as we're comfortable with all those numbers, let's talk about the distinction between a valence electron and a core electron. So what is a valence electron? What does that mean? Okay, so one way to think about it is that it's the last shell that's filled. What do valence electrons do? How do we typically describe their behavior? Valence electrons are the ones that what? Yeah, they participate in bonding. So we might gain them, we might lose them, we might share them, but valence electrons are what we consider the outermost electrons, the ones that deal with bonding. In terms of the energy level that the valence electrons live in, do valence electrons typically live in the higher energy levels or the lower energy levels? Higher energy levels. So they're typically going to be closer to the outside, which means they're going to live in the higher energy levels. So if we just look at this electron configuration here, okay, we should be able to figure out where our higher energy level orbitals are. Or conversely, we can think about where the lower energy level electrons are, okay? So a core electron is one of these lower energy level, kind of the ones that are shielded and tucked on the inside. So if you had to pick the lowest energy or core electrons, where would you say they are for hafnium? Where are the core electrons? 6s. So what do the numbers like 6s and 4f and 5d, what do those big numbers represent? Do you guys remember the quantum number n? What does that mean? What does that stand for? So principal quantum number, the energy level, something like that. So something that's got 6, so 6s, that's actually a higher energy level than something like a 4f. So you consider the 4f the lower energy, so that would be core. And we always talk about a noble gas core, and remember that includes everything like 1s all the way through to 5p. So that's going to be core. So anything with the lower energy levels, the smaller numbers, those are going to be core. So the xenon core and then the F orbitals, those are going to behave like core electrons. And again, what you need to be understanding of is that even though the F electrons got filled after the 6s, you should still be able to see that because it's a 6s, that's a larger principal quantum number, so that's why we consider that higher energy. Even though it filled differently, that's why it's the higher energy. So we would say that in terms of valence electrons, we would consider these guys and these guys as our valence electrons. So how many valence electrons is hafnium going to behave as though it has? Yeah, it's going to behave like it has 4 valence electrons because those are in the higher relative energy levels. Questions about how that one works? Yeah.
So why is it like broken?
Why isn't it just the 6s?
Yeah.
So they kind of hint in the earlier part of the problem that hafnium behaves a lot like titanium, and titanium is above it here. Okay, and based on what you know about transition metals, you know that transition metals oftentimes have multiple possible charges. So because of that, they behave like their s electrons are valence electrons, and we know that they lose those first, but we also know that they can lose their d electrons, so we know that d electrons also behave like valence electrons for transition metals. So s and d are behaving like valence. And that's why the transition metals are so hard to memorize, because it's like, oh, it could do this, or it could do that, because it's kind of got different options from where to lose its electrons from. Yeah, of like transition metals being weird.
Well, yeah.
I mean, it essentially would work the same way. The F electrons are typically going to be considered core electrons, ones that have to go through that. But if you think of something like, let's do the electron configuration for iron. That's a good one. So go ahead and take a second and just write out the configuration for iron, and then we'll talk through what that means. All right, so if we're writing the electron configuration for iron, what would you write for that? You start with argon, and then 4s2, 3d6. Okay, so you're used to seeing one possible charge on iron is iron 2 plus, right? That's a pretty common charge to see on iron. Which electrons would have lost to become iron 2 plus? The S, yeah. So this is one way to get iron have a positive charge. What's the other charge you possibly see on iron? Yeah, you also sometimes see iron 3 plus. So it must have lost that other electron from the d orbital. And the way to think about this is you know that there are how many d orbitals? So it holds 10 electrons, and since the d holds 10 electrons, how many orbitals is that? 5. So if we drew it out, 1, 2, 3, 4, 5, and we filled it, we'd go 1, 2, 3, 4, 5, 6. So does it make sense that if it becomes 3 plus, it would kick out that guy? So that's why your transition metals kind of behave like these are valence electrons, but it also can behave like it's d electrons or valence electrons. And it helps us understand the different charges they can have. Other questions about that? Any vocabulary questions with any of that stuff? Yeah. So the core electrons for iron, you would typically just say that, yeah, argon would be the noble gas core, and that's all we'd really worry about. Yeah, even though it doesn't usually lose the rest of these electrons, it can lose from that shell. Yeah, so the trick with the half-new one was really just to consider the relative energy of the F block. And I know we don't often deal with F block elements. Other questions? Okay, the next most popular one was sigma and pi bonding, so let's jump to that. Okay, let's talk through these because most of you guys have them, and then we'll go through and talk about the idea of geometry. So almost everyone I looked at had found all 5 of the carbons, so nice job with that. Again, it's just a shortcut chemists use. You're probably learning that we use a lot of shortcuts for things, but that's a really common one, that we won't draw in carbons, you just have to understand. So 5 carbons there, and then if we count the sigma bonds, what was the number you guys were getting? How many sigma bonds? 16, yep. So the way I told you guys that I think about sigma bonds is that every single bond is a sigma bond. So if you go through, you can count all of the single bonds, and those are sigma bonds, okay? Sigma bonds form from what we call direct or head-to-head overlap, which essentially means you've got orbitals, and if we've got, let's say they're just shaped like this, I'm not representing any orbital in particular, but essentially you've got 2 orbitals that are touching each other, okay? And so your book also probably talked about the idea that your single bonds can kind of rotate, okay? So we can have things going in different directions because the sigma bonds have this direct overlap. With a pi bonds are formed from what we call unhybridized p orbitals, okay? So hopefully you guys remember that p orbitals are these things that look like peanuts. That's how I remember them. Okay, so if I've got 2 unhybridized p orbitals, they can't directly overlap each other because let's say they're got a carbon atom in the center of each of them. So they can't come touch each other because the carbon atoms can't come touch each other. But the way we think about pi bonding is we think about their electron clouds kind of overlapping and sharing what we sometimes call side-to-side overlap, okay? So that's what a pi bond is, and it happens above and below the plane of the bond. And then right in the middle, and I'll use a different color, we have sigma bonds tucked inside there. So I realize I'm not a great artist, but you can see these pictures in your book, and they're pretty similar. So inside every double bond, we say that we have one sigma bond and we have one pi bond. So you should have found a total of 4 pi bonds because there are 4 double bonds in the molecule, but you should have also understood that you get to count the double bonds also for the sigma bonds. So take a second, look at those numbers, go ahead and count through your structure and make sure you can see where the 16 and the 4 are coming from. If you're not seeing it, just ask and I'll explain it again. Okay, so let's talk about the next part of this. Is this molecule generally flat or not? So when I talk about the molecule being flat, I'm talking about its molecular shape. So you guys remember talking about like tetrahedral or bent or trigonal planar, trigonal pyramid, things like that. So what I want you to think about is at each of these atoms here, what is the shape around it? So if I start with the nitrogen up here in the corner, okay, so this nitrogen up here, what can you tell me about the shape around that nitrogen? How many bonds would it have? How many lone pairs would it have? What do you think? How many bonds can you see? 3 bonds. Is there a lone pair of electrons on that nitrogen? Yes, there is. So if nitrogen only has 3 bonds, remember it can't only have 6 electrons around it, so it's actually got a lone pair of electrons that we're not seeing. And again, you'll notice chemists tend to be lazy, especially when you do organic chemistry. We tend not to draw in the lone pairs of electrons because you can kind of figure them out. So if I know that that nitrogen has 3 sigma bonds, 3 single bonds around it, and a lone pair of electrons, what's the shape you've been talking about for something that has those 4 electron domains, 3 bonds, 1 lone pair, but when one of them is that lone pair? What shape has been thrown out there? Yep, so if you have 4 domains, that's tetrahedral, but if you replace one of them with a lone pair, it's a trigonal pyramid. Is that sounding familiar? Okay, so would you consider a trigonal pyramid to be flat? No, it's a pyramid. So I'd say that that section of the molecule is not flat, it's a pyramid. All right, what about this carbon right here? Okay, do you think there's a lone pair of electrons on that carbon? No, why not? Because it does have 4 bonds, right? Remember that double bond still counts as 2 pairs of shared electrons. So carbon only has 3 bonds to it. What's the shape around that carbon atom? It's trigonal something. It's only got 3 bonds around it. It's trigonal planar. Well, if something's trigonal planar, does that sound flat? Yeah. And if you follow around the ring, you'll see that most of the stuff inside the ring is going to be trigonal planar. So if most of the stuff in the ring is trigonal planar, that means that most of this molecule is flat. So that's how we can use geometry to figure out what this molecule looks like. Even though not every single piece of it is flat, for the most part, around the rings, it's going to have trigonal planar or sp2 hybridization, and that allows us to know that this molecule is mostly flat. Any questions about how I'm able to pick that up from the molecule and the bonds? Are there any specific atoms you want me to go through the shape of? You're not entirely sure? Yeah.
So is that double bond on the carbon, right where the ring starts there, so does that not come into play when you're talking about the shape of it?
Like the fact that this is double bonded?
Yeah.
It only counts as 1 domain. So we'd say that that carbon has 3 domains, and when something only has 3 domains, that's the trigonal planar.
Okay.
So you're right, we don't count it as anything special. It's just 1 domain where electron density is. That's a really good point. All right. We did have a couple questions about hybridization, so I'll go ahead and kind of roll all of that into this as well. So when we talk about hybridization, the big ones you need to worry about are sp, sp2, and sp3. So essentially what that tells you is how many orbitals have been mixed or hybridized together in order to form the number of domains we have to work with, okay? So an easy way to think about this is if you know the shape of a molecule, you can kind of work backwards and figure out the hybridization. So for sp3, you tend to have 4 electron domains. And the easy way to think about that is that sp3 hybridization is made up of 1 s orbital and 3 p orbitals. If I mix 4 orbitals together, I'm going to get 4 electron domains. Okay? So when something has 4 electron domains, what's the general shape of that? Tetrahedral, okay? So if I see something that's tetrahedral, it's likely going to be sp3 hybridized. So these all kind of play in together. Okay? sp2 hybridization is a combination of 1 s and 2 p's, just like it sounds like. So how many electron domains would we expect? Exactly, 3 electron domains. All right, and here's where there's this extra layer here. So I said that I've used 1s and 2 p's. Well, how many p orbitals are there? So it holds a total of 6 electrons, because we know that it goes across 6 times. So if it holds a total of 6 electrons, how many total p orbitals are available? 3 are available. So if I'm only using 2, what's this last guy doing? Nothing. It's what we call an unhybridized p orbital. You remember me saying that earlier? What can I use unhybridized p orbitals to do? Form what kind of bonds? Pi bonds. Yeah. So hybridization is related to bonding patterns. So if you're sp2 hybridized, you have 3 domains. If you have only 3 domains, you're typically something like trigonal planar. And if you're something like trigonal planar, typically, for example, the carbon atom we were looking at, that's because you have an unhybridized p orbital available to start forming pi bonds with. So it all kind of starts meshing together. So I would say that this nitrogen here is sp3. I would say that this carbon here is sp2. Questions about those two? All right, let's go one more. If I'm talking about an sp hybridization, I'm mixing together 1s and 1p. So how many electron domains would you expect? 2 domains. If I'm only using 1 s orbital and 1 p orbital, how many p orbitals are left over? 2. If I have 2 unhybridized p orbitals, how many double bonds can I make? 2 double bonds. So that's one thing you might see. You might see something like carbon double bonded in both directions. That would be an sp2 hybridized carbon because it's using one of its unhybridized p orbitals to make one double bond, is using the other one to make the other double bond. The other thing you could see if you have 2 unhybridized p orbitals to work with is you could combine them on top of each other. What would it look like if I had 2 pi bonds on top of each other? What kind of bond is that? It's a triple bond. So that's the other thing you can do with sp hybridization is you could have carbon triple bonded to something and single bonded to something else. Both of those would be sp hybridization around that central carbon. And I can tell that because it has 2 unhybridized p's left over, which you can use to make either 2 double bonds or 1 triple bond. Can you see how those both only have 2 domains off of that central carbon? So that's, again, how the shape helps you understand hybridization. They all kind of work together to explain the same ideas. Any questions about that? So if we're talking about something that's sp3 hybrid, how many electron domains are we worried about? And I can tell that because it's made up of 1s and 3 p orbitals. Since it's made up of 3 of these orbitals, I know that, 4 total, 3 p's and an s. Since it's made up of 4 orbitals, I know that I have to have 4 electron domains, okay? If I've got 4 domains, what's the general shape that 4 electron domains take? Tetrahedral. Remember the prefix tet means 4? If you played Tetris, it's because everything has 4 blocks in it, so tet means 4, so tetrahedral, 4 domains. Okay, but it doesn't just have to be tetrahedral. There are things that have 4 electron domains, but they're not all bonds. So tetrahedral is really only when all 4 are bonds. What if 3 are bonds and 1's a lone pair? Then what do we call it? So tetrahedral, and again, I'm not an artiste, but so that's all 4 bonds. What if that top one was a lone pair? What would you call something like that? Other than a sad octopus? Yeah, it's a trigonal pyramid. Okay, and if I replaced 2 of those with lone pairs, what would you call that? It's going to be bent. So linear really only happens if you have like 6 domains and 4 of them are lone pairs, or 5 domains and 3 of them are lone pairs. But for tetrahedral, there's no possible way to arrange those 4 things linearly. It always goes to bent. So really what we need to do is we need to figure out which of these things has the 4 domains, okay? So you guys ruled out some of them, which is great. So which of those can it absolutely not be? Yeah, it can't be SF6 because that's going to have at least 6 domains. What else can't it be? Can't be PCl5 because that one's going to have at least 5. Now it might have 6 if there's a lone pair on it, but we know that it's got more than 4. So you guys are mostly able to narrow it down between B and D. And the reason it can't be HCN is because that guy looks like this. Okay, so that's linear. It really only has 2 domains. So if we were going to draw BF3 and NH3, they're going to actually look, I wouldn't necessarily say exactly the same, but they both have 3 bonds coming off that central atom. But boron is one of our exceptions to the octet rule. Boron is completely fine with only making 3 bonds. Nitrogen is not, okay? So if we know that boron is not going to have a lone pair, but nitrogen is, which one of those is actually the sp3 hybrid one? Yeah, the NH3. So the nitrogen in the middle is sp3 hybridized. Just to check, what would you consider the hybridization of this if it's only got 3 electron domains? Yeah, we consider the boron sp2. And just so I can really mess with you guys, what would you consider the hybridization of this carbon here? It's sp. So how many unhybridized p orbitals does it have? 2, and what is it using them to do? Make a triple bond, because a triple bond is made up of how many sigma bonds? 1, and how many pi bonds? 2, and what did it make those 2 pi bonds out of? It's all coming full circle. What do we make pi bonds out of? There's sigma inside them, but pi bonds come from those unhybridized p orbitals. And we know we have unhybridized p orbitals because we know that it's only sp hybridization. So it should all connect. It should all sound like one big, very well-constructed lie, right? Everything fits together. So the reason I'm calling it one big kind of lie is because I'm sure Dr. Knyazov mentioned that molecular orbital diagrams are probably the best way to really figure out what's going on in an atom. But these are really nice stories that do a very good job explaining what we see, which is why we still teach them, because they're a little easier to understand and they do explain a good chunk of reality. MO diagrams explain more of reality, but this is pretty good for now. Any questions about the hybridization stuff? All right. First thing you're going to notice, and I know it's teeny tiny, is that I've given you places to put electrons that are in 2 s orbitals and 2 p orbitals, okay? So the first thing we'd think about, those black lines on the side, those are going to be for the individual nitrogen atoms, okay? So do you know, or do you have a periodic table in front of you, how many electrons does a nitrogen atom put in its 2s orbital? Let's try it this way. If I was going to write the electron configuration for nitrogen, how would I write the electron configuration for nitrogen? What noble gas comes before it? So it's got core electrons and helium, and then I'd write 2s2, 2p3. All right, so if I'm doing it like that, how many s electrons does nitrogen have? 2. Does that make it a little more obvious? Okay, why am I doing my arrows like that? There's 2 electrons, but why didn't I just do 2 up arrows? They have to have opposite spins in order to be hanging out in the same orbital. Right, okay. So each nitrogen has 2 s electrons. How many p electrons does each nitrogen have? 3, and we can tell that by looking at the configuration. How should I put those 3 p electrons inside my 3 p orbitals? Yeah, I have to fill across first. Why do I do that? So we got all sorts of fun laws for that. Electrons are negative. They don't necessarily want to be by each other unless they absolutely have to be. And when we force them to be, that's why we do the opposite spins. Okay. So all you really do at this point is you figure out how many electrons are in your atomic orbitals, so like the 2s electron, and then you mix them to form MO, or molecular orbitals. So we're going to take our nitrogen atoms and mix their electrons to make a nitrogen molecule. All right? So if I look at the 2s electrons here and the 2s electrons here, that's a total of 4 electrons. You with me? 2 from each nitrogen. When I fill the molecular orbitals, I start with the lowest energy, which is down here. And what's the most amount of electrons I can put on that line representing one orbital? Only 2. Works just like an atomic orbital. So the next 2 have to go the next energy level up. Are we okay with that? What does it mean that this is sigma and that's sigma star? What does the star mean? Anti-bonding, okay? So we have what we call constructive overlap, where they make a bond like we're used to, and destructive overlap, where they basically don't make a bond. All right, so that's how I put those 4 electrons in the middle. Any questions there? Okay, let's do it for the p electrons. If each nitrogen brings 3 p electrons, how many total p electrons do I have to work with in my molecular orbitals? 6. And again, we're going to start filling from the lowest energy first, and we're going to go up. So take about 10 seconds, talk to your neighbor, figure out how you would put them in that diagram. All right, so we're going to start with the lowest energy first, which is that pi MO. Since those 2 bars are on the same level as each other, just like I do when I fill normal p orbitals, I'm going to fill them separately before I fill them together. So here's electron 1, 2, 3, 4. So far, so good? Where did the next 2 go? Next orbital, right? 5, 6. So that's it. That's all the electrons represented in that. And I have filled, starting from the lowest energy MOs, going up to the higher energy. All I do now to do bond order is I figure out how many electrons are in bonding orbitals, subtract that from the number of electrons in anti-bonding, and I divide by 2. All right? So my bonding orbitals are represented by the blue color. Notice that they're lower energy, and my anti-bonding are the red. So how many electrons do I have in bonding orbitals? Yep. How many do I have in anti-bonding? And if I divided all of that by 2, what would I get? So that's my bond order. So what does that mean? What does a nitrogen molecule look like? What kind of bond does it have? It's a bond order of 3. That look familiar? Yeah, so the bond order tells us exactly what it looks like. If I were going to do N2+, what's the only difference? What does the positive charge mean? Do it with 1 less electron. And where would I rip that electron out of? The sigma MO that come from the pi, because that's the highest occupied orbital. So essentially you just remove the highest energy electrons, just like we always talk about when we remove electrons. Any questions there? All right, that's all I got. I'll see you guys next week for a quiz.